Welcome everyone to another instance of the string Fino seminar. So today we're very happy to have for the first talk Daniel Baldwin from King's College and ICTP, talking about Coulomb and Higgs phases of G2-Manifolds and flat connections on compact three manifolds. So please, Daniel, go ahead.
Okay, yeah, so thank you to the organizers and for the opportunity to present this work. So this talk will be presenting work done in these following two papers, but mainly concentrating on this first one highlighted in blue. And it's a collaboration with Bobby Acharya. And what we do is we physically interpret some G2 orbifolds that can be desingularized to smooth G2 manifolds by a theorem of two mathematicians, Joyce and Karigiannis. And so what we'll be doing is looking at the four-dimensional physics we get from compactifying M theory onto these orbifolds. So a brief, sorry, I've just got to move my cameras, there we go. A brief summary of the results for the simplest case is for a given G2 orbifold with A1 singularities that satisfy some conditions, the construction of Joyce and Karigiannis gives rise to different topologically distinct desingularisations of the same G2 orbifold. And we give these different desingularisations a physical interpretation as different branches of the vacuum moduli space of some four-dimensional gauge theory. And then as a bonus, we also derive some isomorphisms between pairs of moduli spaces, namely the moduli space of flat AD connections on compact flat three manifolds, and the moduli space of Ricci flat metrics on these G2 orbifolds in question. Okay. So in the following, I'll describe in more detail with an explicit example how these topologically distinct desingularisations can arise and how we can physically interpret them in the way that I said. But before this, I'll go over some motivation and background material and give an outline of this theorem of Joyce and Karigiannis. Okay, so some motivation. So we'll be considering M theory compactifications. And since M theory lives in 11 dimensions, to get four-dimensional physics, we have to compactify the theory on a seven-dimensional compact manifold, which I'll call X7. And usually we'll just take our 11D space-time to be 4D Minkowski times this compact seven manifold. Then if X7 has a Ricci flat metric, this space-time automatically solves the 11D vacuum Einstein equations. So why G2 manifolds? So firstly, G2 manifolds, what I mean by that is just a seven-dimensional manifold whose holonomy group is contained in the Lie group G2. Now these are good models for the extra seven dimensions of M theory, and the reasons are that they're necessarily seven-dimensional. They are Ricci flat, and when you compactify M theory onto them, you preserve n=1 supersymmetry. But it's not enough just to consider smooth G2 manifolds. In fact, in order to get things like non-abelian gauge groups in 4D and chiral fermions, you actually must have singularities on the space. And so in this talk, we'll be concentrating on codimension 4 ADE singularities. So G2 orbifolds with codimension 4 ADE singularities. And these are what give rise to non-abelian gauge symmetries in 4 dimensions. Okay, so understanding the physics of G2 manifolds and the singularities that they can develop is important and interesting physically. And also G2 manifolds are an active area of mathematical research as well. Now, since the interesting physics happens around these singularities on our G2 orbifold, it's convenient to zoom in on the singularity of interest that we want to study and work with this local model space. So ADE singularities, which we'll be focusing on here, occur along three-dimensional submanifolds, which I'll call Q, inside our G2 manifold, or inside our G2 orbifold, sorry. And nearby Q, X7 will look like Q times some ADE singularity, where an ADE singularity is C2 modulo a finite subgroup of SU2. So what physics do ADE singularities give us? Well, if we take M theory on seven-dimensional Minkowski space times an ADE singularity, we get seven-dimensional super Yang-Mills in the 7D spacetime. with gauge group GADE, where GAD is the group that corresponds to the finite subgroup of SU2 by the McKay correspondence. So, for example, if we had M theory on a C2 mod Z2 singularity, we'd get 7D super-Yang mills with gauge group SU2. Then further, if we take M theory on 4D Minkowski times Q times an AD singularity, we get some 4D supersymmetric gauge theory that arises from the reduction of 7D super-Yang mills on the 3-manifold Q. So this is where our 4D gauge theories are going to come from. But more generally, we might consider some space Q times an AD singularity or modulo some finite group K with some G2 holonomy metric on it, where K here acts freely on Q so that we don't get any extra singularities. And these sorts of singular sets occur in examples of G2 orbifolds. And the desingularization of such a space is interesting physically because we want to understand the whole moduli space of our arising 4D gauge theory. And as we move around this moduli space geometrically, this corresponds to singularities either appearing or being resolved. So these mathematicians, Joyce and Karigiannis, showed that this can be done for G2 orbifolds which have singular sets of this form in equation 1, but specifically for the case where gamma AD is Z2, and also this K is Z2 as well. So I'll just now briefly outline what their theorem says. Okay, so not too long ago, they published some new construction of smooth compact G2 manifolds. As a starting point, you take a compact G2 manifold and you assume it to admit some involution I, which preserves the G2 structure. And then if you quotient by this, you obtain a G2 orbifold. And the fixed point set of this orbifold is a 3-dimensional submanifold Q, and the singularities locally look like Q times an A1 singularity, C2 mod Z2. They then show that if on Q there exists a harmonic and nowhere-vanishing one form, then you can resolve the singularities of the space by removing some neighborhood of the singular set and gluing in a family of Iguchi-Hansen spaces, the size of which is governed by the norm of this one form. So Iguchi-Hansen spaces are just the desingularization of a C2 mod Z2 singularity. And they then prove that this smooth 7-manifold they get has G2 holonomy. But in fact, they actually say something more general. So if everything still goes through, if you take just a general G2 orbifold, it doesn't have to globally be a quotient. As long as the singularities look like, as long as the singular set looks like Q times an A1 singularity, and as long as Q has this special one form living on it. And secondly, everything still works if you replace this one form with a one form defined up to a sign locally on the 3-manifold. So this is what we'll call a Z2 twisted one form. And this latter point is important because this Z2 twisted construction is actually where these topologically distinct desingularizations that I mentioned before are going to arise from. And so physically interpreting this is the goal of our work. And also generalizations of this Joyce-Karigiannis construction are natural in our framework, so we can easily consider more diverse ADE singularities and also higher order twists than just Z2. We could also think about Z3 twisted one forms, for example. Okay, so just to summarize what I said, we want to physically understand these spaces X0, which look like Q times an AD singularity mod K, where Q is some 3-manifold, and their desingularizations, which I'll call X tilde. And then we'll perform Kaluza-Klein analysis to identify what fields we get in massless fields we get in 4 dimensions from the M theory compactification. And we want to study this theory's vacuum moduli space. And we'll see that we can do this in 2 different ways. One way is by considering the moduli space of G2 holonomy metrics on the resolved space, X tilde. And the other viewpoint will be to consider the moduli space of flat complexified ADE connections on this 3-manifold Q mod K. And we'll see that this first viewpoint will involve considering K-invariant configurations of points in R3, which is quite a simple space to consider. So now we'll look at some simple example of a local G2 orbifold of this type, and this will illustrate all the ideas. Okay, so as a first example, we'll take our 3-manifold Q to just be the 3 torus, and then we'll take our G2 orbifold to be T3 times an AN-1 singularity or mod Z2. And we take the Z2 to act freely on the T3. So it acts as minus, minus, plus, but with this shift on the third coordinate. Then we can, make this orbifold into a G2 orbifold by putting a G2 structure on the space. A G2 structure is just a special 3-form. So this is the 3-form that we can put on this space, where these omegas are the hyperkähler 2-forms on C2. And then the metric is just the flat metric on T3 and the Euclidean metric on C2. The action of Z2 on C2 is given by the fact that we want to preserve this G2 structure. And so Z2 must act on C2 as -1 on 2 of the hyperkähler forms and 1 on the other one. So an example is just Z1 goes to minus Z1 and Z2 is left invariant. And then on this space, we can see that T3 mod Z2 has a single harmonic 1-form, dy3, and 2 Z2 twisted harmonic 1-forms, dy1 and dy2, because these are defined only up to a sign in the quotient space. And these are all nowhere vanishing. So we're in the realm of this Joyce-Karigiannis theorem. So following Joyce and Karigiannis, we should replace this singular set with its desingularization. So this is going to be T3 times n-centered Gibbons walking space, or modulo this Z2 still. And I'll review the geometry of n-centered Gibbons walking space in a couple of slides. But what we don't know is how this Z2 acts on the n-centered Gibbons walking space. We only know how it acts on the singular space, C2 mod Zn. So in a paper by Dominic Joyce, it's explained that the action of a finite group on the desingularization of some ADE singularity isn't necessarily determined by the asymptotic conditions on it. But in fact, the extra data you need to determine the action is a homomorphism from the finite group K into the Wahl group of the corresponding ADE Lie algebra. And so there could be several different Z2 actions on this n-centered Gibbons walking space, differing by elements of the Wahl group. And these are what give rise to these topologically distinct desingularisations. So just, keep in mind that the Wahl group plays a role here. So just to illustrate this, if we take n equals 2, so we're back to A1 singularities, then the Wahl group is Z2, the Wahl group of SU2 is Z2, and also our group K is Z2 in our example. So we're looking for homomorphisms from Z2 into Z2, and there's only 2 possibilities. Either we map the generator of the first Z2 to the trivial element, or we map it to the generator of the second Z2. And in fact, the generator of the Wahl group here reverses the orientation of the 2-sphere at the center of a Gucci-Hansen space. So this means we get 2 different Z2 actions. One of them acts trivially on the second homology, because the second homology is generated by this 2-sphere. And the other one acts as -1 on the second homology. And so we get 2 topologically distinct desingularisations, depending on which Z2 action we choose. So I'll label these by C and H for Coulomb and Higgs, which will be explained later. So now just quickly review this n-centered Gibbons walking space. So it's a 4D hyperkähler asymptotically locally Euclidean manifold. And the metric and hyperkähler forms are given here. So in this metric in equation 8, x is a coordinate on R3, and t is a coordinate on a circle. And v here controls the size of this circle. So the space almost is like a circle bundle over R3. But at these points, little a, the circle degenerates to 0 size because this v blows up. So these little a's, we have n of them. These are what we call the centers. And at each of these n points, the circle fiber pinches off to 0 size. So if we take the line segment between any 2 of these centers in R3 and take the pre-image of it, topologically that is a 2-sphere because these circles pinch off at the ends. And if we take the collection of all of these 2 spheres from adjacent or consecutive centers, generates the second homology of the space. And the topological intersection of all of these 2 spheres is minus the Cartan matrix for the AN-1 Lie algebra. And we're going to get Z2 invariant and Z2 twisted two forms in our space from the Poincare duals of Z2 invariant and Z2 twisted linear combinations of these two spheres. So this will be important when we do the Kaluza-Klein analysis, because we essentially are just counting harmonic forms. No, sorry, these two forms are harmonic as well. Okay, so we want to realize this Z2 action on the coordinates of n-centered Gibbons-Hawking space. And by requiring that we preserve the G2 structure on T3 times Gibbons-Hawking space, we're led to the conclusion that the Z2 must act trivially on T. It must act on the R3 coordinates of Gibbons-Hawking space as an element of SO3, and it must leave the potential V invariant. And leaving the potential V invariant occurs if and only if K preserves the set of centers. So just in summary, Z2 must act on Gibbons-Hawking space as an element of SO3 on the R3 coordinates, and it must send all of the centers into themselves somehow. Okay, so now we're going to study the moduli space of our 4D gauge theory that we get from the M-theory compactification, and then we'll describe its field content afterwards by doing Kaluza-Klein analysis. So one way we can study the moduli space is by studying the moduli space of G2 holonomy metrics on our G2 manifold. And this is, because we're just taking the flat metric on the 3 torus, this is given by, this moduli space is the same space as the Z2 invariant Ricci flat metrics on the n-centered Gibbons-Hawking space. And from the previous slide, this space is exactly the same as the space of Z2 invariant configurations of n points in R3. So as an example, if we take n equals 2 and we choose our Z2 to act on the R3 coordinates of Gibbons-Hawking space as minus, minus, plus, so just the diagonal SO3 matrix, minus, minus, plus, then there's two possible configurations that are Z2 invariant of 2 points. So the first one here has two parameters, and the Z2 action swaps these 2 points. And so the 2 sphere coming from the line segment between them has its orientation reversed. And in the second case, we put the points on the axis of rotation, and they're left invariant, and the 2 spheres coming from the line segment between them is its orientation is preserved as well. So we have one 2-dimensional branch and one 1-dimensional branch to the moduli space. Another way that we can study the moduli space is by thinking about them, the space of flat connections on this 3-manifold T3 mod Z2. So it's known that the moduli space of M-theory on orbifolds of this form is given by the space of flat complexified ADE connections on the 3-manifold, which in this case is T3 mod Z2. So for this case, if we take n to be 2, the moduli space is given by the space of flat complexified SU2 connections on T3 mod Z2. But the space of flat connections is precisely given by the space of homomorphisms from the fundamental group of T3 mod Z2 into SL2C, which is the SU2 complexified, modulo conjugation by this same group. And so we can just compute this. And also this point of view gives us information about the 4D gauge group. So at some point on the moduli space, the gauge group in 4 dimensions is given by the subgroup of SU2 that commutes with the flat connection. So I'll talk about that when I go through this now. So let's compute this moduli space first. So the fundamental group of T3 mod Z2 is given here in equation 15. So it's got 4 generators. And we want to look at how many ways we can map these into SL2C matrices that satisfy these same conditions here. So one possibility is this identity connected branch here. So all the matrices are diagonal, and there's a single parameter, θ3. At the origin of this branch, all of SU2 commutes with these matrices, because everything's just the identity. But if we go to a generic point on the branch, then only a U1 subgroup commutes with these matrices. So this will be the gauge group at the different points on this branch. Another possibility is not identity connected, and it has 2 parameters, θ1 and θ2, and the beta matrix now is off diagonal. So at the origin of this branch, only an SO2 subgroup of SU2 commutes with these matrices because this beta is off diagonal. And if we go to a generic point, nothing commutes with these matrices. And it's important to note here that the beta matrix is in the Weil group of SU2, or at least in the normalizer of the maximal torus. And so this harks back to what I said before about the Weil group playing a role in these different branches. Okay, so we can see that these two viewpoints agree. So we have two different branches. One of them's two-dimensional, and one of them's one-dimensional. Okay, so now we can look at what the physical theory actually is on each of these branches. So to work out the massless field content in 4 dimensions, we have to do Kaluza-Klein analysis, which is just counting the harmonic forms on our compactification manifold. And so the massless bosonic fields are going to come from expanding the 3-form field of M theory in terms of these harmonic forms. So we'll get massless gauge bosons from any harmonic 2 forms and massless scalars from any harmonic 3 forms. And the number of harmonic 2 forms we get depends on the number of even linear combinations of, or sorry, Z2 invariant linear combinations of 2 spheres on this Gibbons walking space. Okay, so yeah, depending on which Z2 action we choose, we'll get different numbers of massless scalars and gauge bosons in 4 dimensions. So just to summarize the theories that we get after doing this, on the Coulomb branch, or what I call the Coulomb branch, at the origin, we have n equals 2 SU2 super Yang-Mills. And if we give a VEV to the adjoint scalar, we break SU2 to U1. And this leaves us with a single massless complex scalar, which was the one complex parameter on this Coulomb branch. On the Higgs branch, however, at the origin, we have an n equals 2 SO2 gauge theory coupled to 2 hypermultiplets, which transform as a doublet. And this is essentially the abelian Higgs model. And if we give a generic VEV to the scalars in the hypermultiplets, we break the SO2 completely, and we're left with just 2 complex, massless complex scalars. And these are the 2 complex parameters on the Higgs branch. Okay. So this is a summary slide of everything we just did, but I think I'll skip through that.
Sorry, Daniel, sorry for the interruption. In about 5 minutes, you will enter your questions time, okay?
Okay, thank you. Okay, so we can also, everything that I just said, we can do all of this for any A-type and D-type singularity of any rank. So the example just used A1 singularities, but we could do any rank. And we can even say a lot about E-type singularities as well. And we could also think about higher order twists than just Z2, Z3 or Z4, for example, and everything still works as well. And also the reason we had n equals 2 supersymmetry in this example is just because the example was quite special, but generically we would have n equals 1 supersymmetry. Okay, so now I'd just like to say something about an isomorphism that we get between different moduli spaces. So if we, just for thinking about the A-type case again, so n-centered Gibbons walking space, if we think about the moduli space of Ricci flat metrics for this more general case, then we need to think about the space of Z2 invariant configurations of n points in R3, and we can completely determine this space in the way that I've argued in these bullet points, but I won't go into in detail. And so this suggests, because we have these 2 complementary ways of viewing the moduli space of our gauge theory, this suggests that we can completely determine all the branches of the moduli space of flat SLNC connections on T3 mod Z2 and the dimension of all of these branches. And so this led us in this second paper to derive some isomorphism between these moduli spaces. So for the A-type and D-type cases, we can completely determine the moduli space of flat connections on any compact flat 3 manifold, T3 mod K, by considering the moduli space of Ricci flat metrics. And so the isomorphism is in this equation 17. And for the E-type cases, we leave it as a conjecture because we're not able to explicitly construct the K-invariant Ricci flat metrics in the way that we can for the A and D-type case, because we don't have this Gibbons-Hawking kind of ansatz for the ALE space. Okay, so that's what I wanted to say there. So we can also think about compact examples. So the example that I was using here to illustrate the ideas was non-compact because we were taking some local model of the singularities. But we could imagine this being the singular set of some compact G2 manifold, and all the results that we have apply to this case. And so we can, take some examples of compact G2 manifolds. So Dominic Joyce has many examples that we could use, and we can completely determine the physics of these. So I'm going through this in not too much detail, but and also we can take some examples by Reidegeld, which have more interesting ADE singularities, and we can use our results to determine the physics of these compact G2 spaces. So like there's this example here that has E6 singularities, 5 over T3 mod Z2 times Z2, for example, or D4 over T3 mod Z2 times Z2. And so we can use our results to look at these as well. So there's some different avenues one can take from this work. So you can try to understand what happens when the harmonic one form on the 3 manifold has zeros. So for the construction of Joyce and Karigiannis, it was crucial that this one form was nowhere vanishing, but you could try to think about what it means when this has zeros. You could also study what happens when you let K act non-freely. In this case, in the G2 orbifold, you'll get codimension 6 singularities, and this has links to 5-dimensional superconformal field theories. And you could also study the heterotic duals of these G2 orbifolds and study the physics from the heterotic string theory point of view. And this is some work that I'm doing at the moment. Okay, so just quickly in conclusion, we've physically interpreted the type of G2 orbifolds that can be resolved by the methods of Joyce and Karigiannis and generalisations of these. And we've seen that the twisted harmonic one forms involved in the construction give rise to non-identity connected Higgs branches of the 4D gauge theory moduli space. We studied this moduli space from 2 different viewpoints, and this led us to discover some isomorphism between pairs of apparently unrelated moduli spaces as a bonus. Okay, so just flash the references we're recording, and thank you all for your attention.
All right, thank you very much for the nice talk. Now we have time for questions. Okay, Ethan, it's a question, so please unmute yourself and go ahead.
Hi, thanks for the nice talk. So do you end up with any cases where the 4D gauge group is non-simply laced?
Non-simply laced.
So
no.
Yeah, like SPN or SO, with an odd number.
No, I don't think so.
I see. So what was I gonna say? The quotient you constructed, this group K, it never acts as an automorphism on the ADE singularity, I guess. It always
no, just as as some element of the Val group.
Okay, yeah. So I think it can be more general than the Val group. You can get these automorphism guys. And then
indeed, actually, and so when I mentioned this work of Dominic Joyce, actually the homomorphism should be from K into the outer automorphism group, semi-direct product with the Val group. Sorry, the you have these you can flip the whole diagram thing. So
sure,
yeah, probably you can say something more general if you consider that as well.
Great. And then my second question is, how would you determine the superpotential for some of these 40 n equal 1 cases?
So we didn't actually do that, so I'm not no, I'm not too sure.
Okay. Oh yeah, thanks.
Okay, thank you for the question.
Right, any further last minute or 10 questions? Okay, if not, then let's thank Daniel again